and today we are going to talk about instance segmentation. So last lecture, which I couldn't take live, but I shared like a video recording with you from last year. That was semantic segmentation, and I hope you went through it because there was some basics there which we'll use in the today's lecture. So before starting the lecture, again a reminder: some of you have not submitted the SPI yet. So if you haven't done that, please do that as soon as possible. All right, so let's start with instance segmentation. Now we have seen, we started with classification, and then we moved into object detection. Then the next part was semantic segmentation, right? Now instance segmentation it's kind of related to both object detection as well as semantic segmentation. Because what we want here is we want each instance of the object category, and we wise like pixel-wise localization of that object. For example, if you have two different chairs in your image, then I want the algorithm to say, okay, this is chair number 1 and this is chair number 2. So the number 1 and 2 doesn't matter. It's just like we should be able to differentiate between these two chairs. And for example, in this particular case, we have 4 different chairs. So we should be able to differentiate between all these 4. We should be able to say that, okay, this pixel belongs to the green chair and this pixel belongs to a blue chair, right? So each instance should be separate. So that's called instance segmentation, and each pixel you should know like which object category it belongs to. And that's why it's related to semantic segmentation. Now, if you look at this picture, so if I just do semantic segmentation, then for example, if I have 3 object categories, I have a table, I have a person, and I have TV, right? So I will get something like this. So all these pixels belong to a table, and all these pixels belongs to people, and this is the TV image. Okay, so this is semantic segmentation. Now, if I have to do instance segmentation, then this is perfectly fine because we just have one table in the current image, and this is also fine. We only have one TV. But in this case, we should be able to tell that we have 3 different people, and we should be able to tell the boundaries, right? So that's the distinction between semantic segmentation and instance segmentation. Now, if you think about this, you can have a very simple solution. You can perform semantic segmentation, something like this at the center, and then you can perform object detection, something like this. And you should be able to combine these two to actually derive this kind of result. Excuse me. So in case of object detection, you know like what's the boundary of each object, right? We have this bounding box, and this boundary you can use to define a boundary between these two, and then you can distinguish between these two people over here. Okay, so that's a very simple trick which can be used to convert semantic segmentation into instance segmentation. And the best algorithm which we have today, it's like mask RCNN. We do have some better, but slightly not like significantly better. So this is kind of the state of the art. It's called mask RCNN, and as the name suggests, we have already covered RCNN, fast RCNN, and faster RCNN, right, for object detection. So mask RCNN is like is the 4th sequence in those 3 algorithms, and in fact it's from 2017, and it was one of the best paper award in that conference. It's like one of the top conference in computer vision. So as you can see that we just talked about how we can use object detection for instance segmentation. So this method exactly does that, because we know RCNN and all those algorithms, they are used for object detection. So it is utilizing those algorithms and refine like these bounding boxes to get these fine boundaries. Okay, so these are some of the results. These are the actual results from this algorithm. You can see it can work pretty well. So if you look at these 2 images on the right here, it's a very crowded scene, right? So lots of sheep, but still the algorithm can detect like very fine boundaries. Okay, even in this case, like all these smaller objects, they are detected. And this is pretty interesting over here, like on the left bottom, you can see like all these people, they are being detected at the background. Not just detected, we have fine boundaries of those people. Okay, so these are some of the examples from this algorithm. So now let's talk about how this algorithm works. So we know how faster RCNN works, right? Now mask RCNN is faster RCNN, exactly the same network which we discussed in one of the lecture earlier. And we just add a fully connected network on these region of interest. So this network is going to take these region of interest and refining them into these segmented boundaries. So we just have this additional branch, and this is a fully convolutional neural network. And if you have seen like lecture from the last class, then you know how semantic segmentation works. Okay, so it's exactly like that, just a sequence of convolutional layers, and the output will be this fine boundary. So this additional thing, and one interesting change is like you might observe here, it's ROI align, it's not ROI pooling. So in faster RCN, we used to do ROI pooling. So we'll talk about what ROI align is and how this is actually useful in finding these finer boundaries. Right? Otherwise, rest of the network, it's exactly the same as faster RCN. Okay, so now first, so this part should be clear. If there is any question, please let me know, because this is just like a convolution network. You take these features and pass these to like a sequence of convolution layers, and those layers will just output this fine boundary. The interesting part is how you actually perform this ROI align instead of ROI pooling, and that is what we are going to discuss in this lecture. All right, so going back to ROI pool, you know that if let's say this is your feature map, okay, so in this case it's 5x5, and this was your region of interest, and this region of interest is actually coming from a region of interest in your input image, right? So, and that's why it's not properly aligning with like these pixel values. And that's why what we do is we try to map these corners with the corners of like the feature maps. So in this case, we try to quantize, match this corner with this one, with this one, and so we try to shift it, right? So that's called quantization, and this is how like ROI pooling works. We have discussed this earlier. Now, what is happening here is the actual region which was at this location, right? This is actually getting missed. We are not getting any features from there, but this was actually part of that region, and we are getting this extra region here, which was not part of the object. So that's like one of the drawback. Now, so this adjustment is not good, because we are kind of I mean, this was good for object detection, not good, but I mean, kind of fine, because we are not finding very fine boundaries, right? But now what we want is we want very precise boundaries around the subject. And if we do these approximations in the feature map, then the boundaries will not be very close to the actual ground truth. So now the solution should be something where we don't have to make such quantizations, such approximations. Okay, so that's where like ROI align comes into picture. So the standard ROI pooling, if this is your input image, this is your original ground truth, and this I think we have covered earlier as well. So you shift it. What will happen is you will lose like this blue region, and you will gain this green region, because you'll have to shift your bounding boxes over to those pixels. And so that was like one step where you lose some information. The second step was when you actually perform the pooling. So the second step was doing max pooling over these pixels, right? So it depends upon like what's your target resolution, what you want. In this case, if you want 3x3, so you'll have to divide the input feature map to 3x3 grid. So in this case, we are completely losing all these pixels. Okay, so these were like 2 steps where we lose some information. Now, a simple solution to this issue is, and the solution is, it's called ROI align. What we do is, we don't quantize. We just create pixel values using interpolation. Okay, so we are not going to actually move or quantize the actual bounding box or the proposal. It will remain where it is. And then what we will do is, whatever target shape we want, for example, if we want, let's say 2x2 or 4x4, we'll just create a grid of that shape inside that bounding box. Okay. So now the question is, if I want a value for this location. So earlier what was happening? Earlier, if you were at this location, we'll just take the pixel value at this location, right? We'll just propagate that. But now you are at this location, so we don't know like what value to take. So what we do is, we perform interpolation and we take values from all the 4 neighboring pixel locations. Okay, so this you might have seen in like the previous lecture where we're talking about bilinear interpolation. And so let's see how this can be done. So this is fine. This is also fine. Okay, so this is the exact example. Okay, so this is your feature map, and this was your proposal. You know, like the height and width, and you don't have to compromise like by rounding it off to 6 or 4. If it's 6.25, perfectly fine. Don't worry about it. And let's say your target feature map size is 3x3. So what you will do is, you will just create a 3x3 grid inside this feature map, and don't worry about alignment. Okay, so far so good. Then what we will do is, then we can easily find out like the height and width of these cells, because we know this is 6.25. You can just divide that by 3, and again you can divide this by 3. So you have the dimensions for these cells, which is also good. Now the next step is, we actually find values for 4 different locations inside each cell. Okay, so now listen carefully. So let's say this was your initial cell. So you create 4 locations exactly like these locations, and these are equidistant. All right, and for each location you are going to create a pixel value which will be coming from 4 neighboring pixels using bilinear interpolation. All right, so before finding the value, let's find out the actual coordinate values of these locations. So this is 9.94, 6.50. So this is corresponding to this initial location here. So this is just x and y. All right, then this is the formula I think you might have seen in the last lecture as well. So you can just remember this. So excuse me. So the way it works is, I can give you a slight intuition so that it helps you in remembering how it works. You have if you have a point, so what this tries to do is, it tries to capture values from 4 neighboring locations. All right, so you have this is the first location, this is the second location. So you can see that this point 1 is coming from here, and point 2 is coming from here. So these are the actual values, actual pixel values. All right, and this 1 and 0.7, it's coming from the other 2 locations. All right, so those are the actual locations which we want. The rest, all these things, you can see these are just weights stating how much of this amount you actually want in contribution when you compute the value at this location, right? And that's how you do interpolation. So if you think about this, you know how to compute weighted average, right? So this is kind of doing exactly the same thing. You're kind of computing weights. How much of 0.1 do you want, and how much of 0.2 you want, and it will depend upon how far this location is from point 1. And these terms, if you will look carefully, they are exactly doing the same thing. So this 10.5 is the location of this point 2, all right? And 9.94 over here is the location of the center point. So if you subtract these two, it's kind of saying how far are these 2 points. And the denominator is just trying to normalize it. So what's like the total distance between these 2 points? So 10.5 is coming from point 2 and 9.5 is coming from this point 1. So it's kind of normalizing so that you don't have issues with like if you have like bigger cells or smaller cells. All right. So this measure tells you how far like this point 1. This might also remind you when you were trying to compute histogram of gradients, right? So how you used to compute voting. So it's exactly the same formula actually. So you compute the normalized distance of the opposite end, right? And that's exactly what it is doing. And similarly, you can observe like the same values here. Okay, and this one is like in the y direction. Okay, so that's bilinear interpolation. That's fine. You can just remember the formula. And once you have this formula, for each of these locations, you can compute a value, a pixel value, all right? Considering like what are the 4 neighbors. And similarly, you can do for the second one, which is over here. So we'll have to first figure out what are the 4 neighboring pixels. So in this case, this is the one, this is the second one. Okay. So you might, so these numbers 0.1, 0.2, you can see that these are actually the features. These are the values in this feature map. So each of these cell will have one value. Okay, so we're just trying to distribute it. Okay, question from Zubin. Computationally, is ROI aligned more expensive than pooling? Yeah, that's true. It's more expensive. But if you think about this, the mathematical operation, I mean, it's just subtraction and multiplication. And you can do this like all in parallel. So when you do this in GPUs, it's highly optimized. It, of course, it's bigger than ROI pooling, but still it's not that much. Okay. Okay, so and similarly, you can get this value. So similarly, we'll get like these 2 values as well. So for each cell, you can compute these 4 values, and then you just perform a max pooling operation. You see that, okay, which of these features is the maximum? In this case, it's 0.51. You just keep that. All right. So for each cell, you will compute 4 numbers, then max pooling, you got the maximum one. And similarly, you will do for the second cell, third cell, so on and so forth. And for each cell, you can get a number. So in this case, you're not losing any information, but if you think about this, you are actually gaining some information. Because when you compute, we're computing this 0.51 here, over here, right? So this 0.51 is coming from these 2 pixel locations as well as these 2 pixel locations. So these 2 are actually beyond the actual boundary, and which is fine. It's actually covering some context, but the good thing is you're not losing anything, and your boundaries are very precise. Okay, so yeah, that's the whole idea about ROI line. And as I said, like it was a pretty interesting idea. This paper got like best paper award in one of the top conference, which is pretty good. Okay, so then once you have this ROI line features, you can just pass this to the convolution head, which will give you the segmentations. Okay, so if you compare this with ROI pooling, you know that you first lose like this blue patch, dark blue, you gain like this green one, and then when you do max pooling, you lose like this again the blue one. Okay, so essentially you are just considering these pixel values. But ROI align, you don't lose anything, you just gain the context, which is fine. Okay, so the final mask RCNN model, as we discussed, the top branch you already know. You predict the classification, the class labels. You predict the bounding box adjustments. This is the additional head over here, which actually takes those features from ROI align And for each extracted ROI line features, pass them to a sequence of convolution layers to predict this mask. So this is one very interesting example. You can see here that so this is the target object, right? So the soft prediction is giving you something like this, all right? And if you resize this, because what is going to happen is when you do ROI align, okay, this ROI align, right? So whatever is the shape of the proposal, you will always make it, mostly we make it square. But of course, when you can make it any other shape as well. It could be 3x5, 3x7. But whatever you choose, it has to be consistent across all the objects, because you can't change your network for different objects, right? So usually we keep it square. So whatever the input shape is, the output will always be square. And since this is square, the input to this network is square, the output is also going to be square. And that's what is being shown here. So this prediction is 28x28. And you can see that it's actually messing up with the aspect ratio. But what we can do is we actually knew, like when we performed ROI align, how much aspect ratio we are distorting. We can scale that back, and this is kind of giving you the resized soft prediction. And of course, you can binarize it, use some thresholding. You can use Otsu thresholding, which you have implemented for programming assignment 3, or you can just use maybe your threshold based on some heuristics, and then you know like the foreground and background, and that's like your final mask. All right, so that was mask RCNN in nutshell, and these are some sample results. I showed you some earlier as well. So this works pretty well, and as I told you, so you can see that these cars, like it's able to distinguish between all these parked cars over here, so which is pretty impressive. Okay, some more examples. And yeah, I think that's all I have for today's lecture. So if there are any questions, and this is the last lecture we'll have in this course, and the final exam will be on 9th. It will start at 4, and it will be 75 minutes, so end at 5:15, and you all will get like 5 additional minutes to submit your paper. Okay, so question from Sean: will final be cumulative? No, so I sent an announcement, I think yesterday. So your final will be based on all the lectures which we have done after midterm and until today. So this instant segmentation. Is it clear, Shane? Okay, so question from no, so yeah, I think if you read the announcement carefully, so those lectures, I think some students were interested in optical flow and some other topics. So I shared like for those students, and whatever lecture we have not covered during the class, it won't be there. So it will be only until instant segmentation. And I think it was action recognition will not be there, optical flow will not be there, and again, I think the last topic was camera modeling. That will also be not covered in the final exam. Okay, question from James: will the final mostly be conceptual, or will it require heavy number crunching? I will say it will be like almost similar to your midterm. So expect like the same difficulty level, more or less, and same type of questions. Okay, question from Daniel: can we get a sample final? Uh, we are not going to release any sample for the finals. Yeah, but I don't know like why you need that, because it's going to be exactly same as your midterm. It's just different topics. So I mean you can take that as a guideline, the actual midterm. So I think that will be a good reference. So we won't be releasing any samples for the finals. Okay, so if there is any question from last lecture as well, I will be happy to cover that. And I think that was also very interesting topic, semantic segmentation. Question from Beyond: Can we have more time than 75 minutes to do the final? So midterm was 60 minutes. So in the final as well, you will have the same number of questions, 20 questions, same difficulty level, but we have increased it to 75. So I think that should be sufficient. So Vayan, you think like 75 minutes is not enough? Okay, so that's good. Okay, question from will there be lots of calculations or just high level concepts? There will be some questions with calculations, and I think same as midterm, the bonus questions will require some calculations, but you are free to use calculator, so that shouldn't be an issue. So yeah, I mean, if you don't know, I mean, you can use calculator. So Conor, yeah, it will be mix of both, but not that many calculations. Okay. All right. So if there are no other questions, I think we can end it early today. So thank you very much for taking this course. I hope you had a very good time, and best of luck for the finals and also your project. Right. Thank you. Bye.